In this example, I'm trying to show how to model a SAGD developer using the Ashaw SemiDynamic Software. In this example, we neglect erosion, and there would be another example that show how to model erosion in the Ashaw package and considering its effect on the performance of flow control devices. Currently, a lot of operators are using flow control devices, or in a short way of saying FCDs, to help to uplift the production rates and better recovery. And this is a good example of putting FCD and see the positive effect. And you see, before putting flow control devices, the plateau was pretty much this baseline, and then after the FCD, after a few times, we see the uplift happening on the rates. And this is a really good example of putting flow control devices, but not always we see the positive effect. And this is a problem with every new technology because there are a lot of unknowns there. So in this case, after putting flow control devices, we see it's declining, and this jump here is just a flush production because of the shutting here, so we can't consider this. And then, so this is the baseline after, and which is dropping massively. This is not because of geology, because these two well pairs are on the same path. This is all about design and operation. And Azure Package really helping in both concepts. So we help service companies and operators having better design, and also help operators to have an optimum way of operation. Azure Package is working based on one big basic, and that basic is near wellbore is different from far field. So we have a near field and we have a far field. And the far field is really just acting as a boundary condition for the near wellbore. And once you want to have the flow control devices, which is small nozzles around the wellbore, you have to capture the near wellbore effect. And Azure Package consider that because it do the different modeling for these two aspects. So really assume we have two jars the simple way. The blue jar is the far field, and the green jar is a near field. And so in this case of SAGD, near field is the liquid pool, and the far field is the steam chamber and the reservoir, which acts as a boundary condition because the pressure at the top of the liquid pool is governed by what you put here, injection rate and injection pressure, and the reservoir supply is provided by reservoir helps your dynamics here. So now we know the basic on the modeling. Now let's do one example here using the Ashaw package. So this is the interface of the Ashaw package. This dots and line is the logo of the Ashaw package. In Ashaw package, currently we have black oil, gas reservoir, and on the isothermal models, and we have thermal models which are SAGD and solvent SAGD. Black oil is conventional black oil, so it model gas coning, every aspects of the black oil. Gas reservoirs is modeled hydrofracturing, proppant transport, everything related to the gas reservoir. It can be shale gas, tight oil, tight gas, everything related to that, like gas condensate, liquid holdup, everything's modeled here. For the thermal aspects, in this case we have a SAGD example that we're gonna do right now, and is a solvent SAGD, which is a big name, but it can be from pure solvent injection, like injecting pure C4 and butane, to having 99% solvent and 1% steam, which never happens, but or other way around, 99% steam and 1% solvent. So it's captured the whole spectrum. Today we're going to model the SAGD developer. So for SAGD we have three options. We have objective design, history match, and node analysis. For objective design, is really once you don't have any history and you just a brand new well and you want to design. So you design it blindly without having any history. Nodal is once you want to model part of the well, not the whole well, and it's just for fast modeling. Once you don't have a lot of thing and you just want to do things quick in 10 seconds, use a nodal analysis. And history match is the example that we're going to run here. That you have a history that you want to honor, and then you want to make decision based on that, and you just want to see how the performance was before, and you want to also see how the performance gonna happens in the future by changing your operations conditions. So now let's do the object like a history match thing. Once you hit that, you have the tree get open, the structure tree of the SAGD solution. So these are the things you have to fill in on the input, and you run and the simulator, and you get these, and give you options for history match here, and then you see the results. So let's get back to the input data. Similar to every simulators, we have to put a fluids, and in SAGD we have a steam that we inject, which is a pure water, which really based on the steam table, so there is no need to put in any value to the simulators, but you need to put your oil. In Azure Package, we makes the life super easy, because in Canada, mostly three main asset reservoirs at Tabasco, Colade, and Lloydminster. You can choose any of these, and for this case, we want to use a Tabasco, but really if you want to do keen about putting your own properties, you can put things here and ask the simulator to history match both viscosity and density, and then use that PVT data for your modeling. But in this case, you just want to use library, and we want to use Athabasca. Grid properties is that you have to put in. All right, and it's a very key thing on modeling flow control devices, because you have to be small enough to capture the dynamics. In this case, we put 6.25, and it can be any number, but you should know that the software is automatically discretize the grids, and really that's the biggest grid that you have, and it's based on your completion. Your grids may get very small, it can be about 1 centimeter, 2 centimeters, but this is about the maximum value you put in. You're gonna see as your grid size. So now let's come to the reservoir properties, and here we're not going to change anything. We trust everything here. This is for more advanced modeling, so let's not care about it, but we have to put a trajectory, and we have injector and we have a producer in the SAG developer, so we have to put both trajectories in. In SAGD, in Ashaw Package, there's option of inputting text files, and also we can copy paste from Excel. So for trajectory, I'm using copy paste from Excel. So for injector, I can get these columns, but the software is smart enough. You don't have to really tie yourself to these columns. You can just say everything, and you come here and you say paste, and you go back on trajectory, and you come here and producer. Um, and you go paste. Okay. But we have to put a start of the completion. And for this case, it's 52574. And it's the same for the injector. And once you put these things in, you can come on developer and see how in the 3 dimensions it looks like. So the bottom one is our producer and the red one is our injector. So, and you see the check mark after we put in things in. In Ashaw, every red minus thing you have to fill in. The yellow parts is optional. If you want to do more advanced modeling or better results, more data you provide, you get better results. You fill in those orange options, but you have to fill in the red options for sure. So for injector BHP, you have the option of putting constant value. In this case, we read file and we use a text. All right. After just clicking on that, you see the BHP of injector basis, the time. We don't put this and we don't put, but we fill in the permeability in this case because we want to use the diagnostic chart in this case. So in this case, we use Excels. And we say paste. All right. Once you hit paste, you see the gamma ray and the software estimation on initial values on the permeability. We're going to talk about this part later on the producer. And you see the check marks here. So that means you're filling. Now we come to the steam chamber. And in Azure Package, you have the luxury of modeling the steam chamber, changing the quality, heat transfer inside the steam chamber, or just simply say, we assume 25 kPa or whatever number is pressure loss from injector to produce to the top of this liquid pool. In this case, we just rely on the default and we are done with the injector. So now we come to the producer. In producer, we have to put a flowing bottom hole pressure, and that's the pressure that you suck the oil into the producer. So we use the text file here, where you also can use Excel, as I said previously. And you have the option of smoothing, but for this case, there's no need for smoothing. But in some cases, they are super erratic that you have to use smoothing. But in this case, it's good enough for us to go. You have a heel temperature, and you can put input the heel subcool, and you can put the input the heel temperature. In this case, we use the heel temperature, and we go on Excel, and use paste. So what you see on my heel temperature, only have the time and the heel temperature, and the software automatically calculates the subcool based on the steam chamber pressure. And this is our heel temperature, and the red part is the subcool. Normally, if you put a mirror here, you can see the symmetry between these two, because normally steam chamber pressure is not changing. So that means the temperature inside the steam chamber is not changing. So the subcool really following the heel temperatures for most cases. So let's come to the liquid pool. And this is the engine of the Ashaw software. And as I said previously, that's the jar that deals with the near well bar and all the dynamics around the well bar. So from the top, we have to fill in the temperature gradient. All right. In this case, we have to fill in the DTS data first, then come to here. So we don't care about this. The default value is 0.35. Let's keep that number. And rel-perm, you can put your numbers under rel-perm, but the key thing that's important for the software is WOR, our water or ratio. In this case, we have to put 2.81 and we say apply. So water cut is changed, and software use that to fit the rel-perm inside the flashing zone. For steam flashing, Ashaw Package currently have two models, coning 1 and coning 2. In the future, I will explain in another example how to model this, what's the differences between coning 1 and coning 2 is. For this case, we go with the coning 1 and assume default value is okay. Now we have to put the temperature profile, and that's the DTS along the producer or the thermocouples along the producer. Currently, a lot of operators have that data. It's getting more common and common. Measuring temperature along the producer. That helps in many operation aspects. And in Azure Package, it helps in modeling a lot. So if you provide those, that really helps. There are different ways of inputting data. Consistent MD, which means that you have constant MD. That means your thermocouples stays there forever at the time of the modeling. You're not taking it, or it's not fading, then you're not removing it. Inconsistent MD, that means your MD is changing. And the last one is very general, that's you put date, MD, temperature. And this is really most of operators provide data in that manner. So we say read file, and we have a DTS data. So once you put this, now you have a lot of data put in here. And you have a scroll bar here, and you can see versus time how the DTS versus the MD is changing. So you can go on and see how that thing's changing, but really you're trying to understand how the data is actually look like. So for example, if you want to see the bad data and you don't want to model that in your modeling, for example 5/26/2019, you see like it's from 21 to 26/2019, doesn't look that these data is valid. So we want to cancel out those. So we come to 5/26/2019 till 21, and we deactivate these data. So we don't want to use these in modeling. The other graph that you want to take a look at is temperature gradient. That's really helps you a lot because it helps you like to see how the temperature are changing along the liquid pool. And so for example, this part I highlighted by using this ball, and it looks like here. And you can see how that things are moving, and you can evaluate how the things are changing in this part. But really that temperature gradients help the software to understand how the heat transfer is growing inside the liquid pool. And Azure Package, there are two temperature gradients. One temperature gradient is before flashing, which is controlled by the heat loss beneath the producer. And normally we don't have that data, but we can use this data, which is based on the DTS, and say, all right, based on this DTS, the user or the software thinks that the temperature gradient. And another temperature gradient happens after flashing. In the flashing zone, that temperature gradient is highly governed by physics and PVT, and they call it Clausius-Clapeyron temperature gradient, which is really the temperature gradient calculated based on the saturation of the steam. So now we have a DTS, we can go back to the temperature gradient. Now we have a data, and we can guess the good temperature gradient for our application. The problem with all the wells, that mostly linear deployed wells, because we put a lot of delta P on the well, and we expose the well to the linear deployed. The temperature gradient we see inside the well, and there's not fall off, mostly dynamic temperatures. They're not really tells us the natural temperature gradient happening inside the liquid pool, and this is basically an artifact of what's happening inside the linear deployed. And this temperature gradient always have to be negative, so you can't put the positive values. And this is statistical suggestions here really doesn't help you on the case of flow control devices. For this case, we go -1, which is about a small value. But for flow control devices, because the liquid pool mostly is very tiny, doesn't change the results that much. So now we have a temperature gradient. We go on the lower completion, which is the key part of the modeling. So we come over here and we say add new completion. And once you put add new completion, it asks you what sort of completion you want to go with. Concentric tubing, parallel dual tubing configuration, or linear deployed. For our case, is a linear deployed. And you also have an option of using the simplified or advanced way of modeling no flow boundary calculations, because between every nozzle there is a no flow boundary that has to be software have to model it for both modeling reservoir and everything happens along it. So in this way we go simplified and we say okay. Now we want to put a date that the completion would be start. So start with the year, we say 2016, and from that point on use a calendar. It's October. It's October 12th. And now we want to put the completion. Okay. So in Azure Package, start from outside to the inside. So start from the outside is a whole condition. So the options here, we have a whole condition. Okay. So for whole condition, we have to say what's the start at, and we have to put the wellbore ID. And now we have to define what is our completion. What's our wellbore looks like. Is a formation collapse, is a cemented, is a gravel pack, or is an open hole. For this case, it's open hole. For open hole, you don't have any property because it's just open hole. There is no property assigned to it. But if you put the gravel pack, for example, this window opens up and you can put the permeability of the gravel pack and those things. Let's put this back to the open hole. Now we want to go to our linear deployed modeling. So let's put a blank part first. So this numbers comes from the wellbore borehole, so it's automatically generated. So this is one joint. We assume it's a one joint, and the length is 27.5. The OD is 6.625, and ID is 605. Oh, I have to redo it's tubing. Tubing in this case means blank hole. And for this case, you have a property. So these are the computation methods for the node analysis, a multi-phase flow inside the borehole. For this case, we use the Bexbury as a default. In new version, we have a mechanistic models, but not in this one. So you can put the roughness or everything you wanted. And so now we want to put the FCDs. And we say how many joints we have. So this is the end of this part. So this 553.29 is 52574 plus this number. And we put the length of every joint. And we put FCD. So now we just want to make our life easy. We just want to put this another blank zone, and we want to put another FCD, and we want to put another blank zone, and then we fill in here. So it's one joint here, and this blank zone is 5336, and this is two joint here, and it's 3-4, and this is the last. And I have to put another FCD to the end, and this is 42, and it's 13.22. All right, now you have to define our FCD, and you can see it says Baker Hughes equalizer helix with the FRR of 0.8, and now we want to change it. So that's the default value. We currently have only two companies here, so let's use the Baker Hughes FCD library. This is select, and it's 3.2, and you can say apply to all the FCDs to the whole completion, and that's really common in all the liner deployed, that we kind of using the same FCD for everything. And you say apply. So we're done. We're done with the completion now. Let's just check everything is fine. Okay. So now let's go to the last step, which we have to put the field or production, because we have to hitch and match our thing. So in this case, we say read files, and we see nothing happens. So in this case, we open the field or production and see what's the format that the timing is. Sometimes the Ashaw package does not recognize the timing, so we have to see how the format is, and then we come here and say, all right, it was DDMD thing. It was day, month, and we have this. Yeah, it was okay. And now we say field load production, and it's populated. So now we have everything in, and if you open up everything, you see you have everything in checkmark. The only thing is we didn't put permeability here, so I missed that. So I have to put the permeability for the gamma ray, and in this case we're using Excel. And we just say paste, and we put this at 0.5. So the cutoff really tells the software the parts they don't want to produce any oil. So if you put a gamma ray of 0, that means everything's producing. For example, you think these parts above 80 is not productive, so you put this as 80, and it tells you these parts are not producing. Okay, for this case, we just put it back to 0, and you just want to say for the first run, yes, it is producing. Most operators are using this log scale permeability versus gamma ray quadratic type equation. And if you have these parameters, you put your own parameters. But if you don't use you don't know those parameters, you can just use this default value and trust the software to gives you optimize this value for your history batch. And this here it gives the option for every grid's permeability. You can change it by hand if you want. You can change. I don't like this value, you put yours. But in this case, we're not doing that. So you don't see the fluctuation because the average for every grid's happening here. So now, other than that, everything is green now. So we can run our simulation. So for the first time we're running, we have to come and start simulation. So we put this here. We want to talk about we want to talk about the rest of the modern aspect. In this case, so we want to explain why it's running. We just want to talk about how the steam flashing and those things are modeling in the Azure package. A steam flashing and gas still solution happens near the wellbore if the PVT force them to. All right, so it doesn't happen every time. Everything is based on the pressure and the temperature at every dimension. So, but if it happens, if you have a gas bubbles inside the oil, it creates a foamy oil. And if you have a steam flashing inside the water, it creates the steam. And that is steam mitigate your rel perm. So that's the bad sign for our liquid pool up dynamic. So how the Ashaw package cares about it? So it says, all right, this is our near wellbore. It does his own PVT modeling or based on the saturation with steam. It calculates the onset of the flashing. And then based on that onset, it calculates how the flashing is happening. And then reduce the rel perm of the liquid in that portion. So it doesn't change the rel perm. This is 1 because everything is liquid here. So, but to understand what's happening inside that flashing zone, you have to do the heat transfer first. I'll talk about these temperature gradient, natural temperature gradient and liquid pool on the time I was explaining the DTS. So the software put the DTS in the period that you have, and based on that, the user or software choose what temperature gradient is, tells you the natural temperature gradient of the liquid pool. This is the red one. But there is other temperature gradient, which we call a temperature gradient of the flash zone. This temperature gradient is really based on a lot of parameters. It's based on the pressure at the drawdown, pressure at the chamber, permeability happening here, the subcool, a lot of things. And then based on that, you calculate the PVT flashing thing. And then based on that, you come up with this temperature gradient. So now let's go back to our software and see how the modeling is. Take it back to here. So this is a run, and what happens here. So these are the dots are the actual data, and the lines are modeled here. So in this example, I'm not talking about history match, but we have two different history matching options, single variable, multivariable, and you can apply the period of time history match. In this example, I'm not going to talk about history matching because I'm going to talk about it on the erosion module FCD pack case. So now we go on the lower completion results. So we have an upper completion, that's a vertical zone. We have a FCD erosion that we're going to talk about it on the FCD example, and the ESB charts. And in the future, we're going to have a PCP for SAGD. So this is date versus time charts. So this is the water, this is the oil, and this is the actual field data. And there's no steam here. And on the bottom, it provides you the well subcool, reservoir subcool, and the drown down. And this is for user to see how the thing's improving on both sides and check the result there. In every chart in the Ashaw package, you have the capability of moving these things if you want to have a better look. And you have a cumulative of everything. But the important part is here. All right, so this is a flux versus MD of water and oil and steam. And this is the pressure. And this is the versus time. So this scroll tells you versus time. You can push it and like see it as a movie. But for this case, we're not doing that. We just want to see how things improving. All right. So we want to see how the water rates, and this is the pressure at the FCDs, and this the blue thing is the pressure at tubing, and this is steam chamber. So this is the pressure at every FCD. To have a better look of FCD analysis, so this is the reservoir drawdown, as a portion of the delta P goes to the reservoir or the liquid pool, and there's a portion goes to the FCDs here. And you can see how that evolving, and this is really tells you to understand your FCD behavior. And these are the cumulative charts. We're not going to talk about it here, but this part is important. This is the temperature of the grid, and this is the sand phase subcool. And in the future example that I'm going to talk about erosion, I'm going to talk about the difference between the sand phase subcool and reservoir subcool and well subcool. But this is the grid temperature. You can see how that's changing. And this is the steam quality at the sand phase. That's the amount of steam quality happens at the sand phase for every grid. So not every case we have a steam coming, but for some cases we have a steam coming. But the important thing is diagnostic chart. So let's take a look at the oil rate versus DPFCD versus DP pool. So for most cases, we design for DPFCD versus DP pool of number 1. That means the pressure drop across FCD is similar to the pressure drop across the liquid pool. That means that's about to be in the middle. That means we're not choking too much, and we let the liquid pool produce, but we're not let the liquid pool to produce as much as it wants. So if the number goes towards 0, that means there is no choking. That means we're getting close to cases like having a liner. That means pretty much no FCD. And if you come to the cases on this case, that means you're choking too much and you're not letting the liquid pool to produce. But we don't know where we want these to happen, all right? So this scroll bar here, it changing the subcool for you, all right? So assume we want to see here, and we want to have the subcool around 1, and these are hot parts. That's the parts we want to have more FCD choking. So in this cases, we have everything below 1, so it's not the optimum design for this valve. We're really looking for the cases. This is type of the thing we're trying to look at, as everything's on the log SK is a linear format. So that means everything's progressing perfectly. But the problem with most cases is, so this is a cold part, so its design is optimum. We have to come and take a look for the cases that we have hottest spots on these sites. So we see in these red parts, we're not choking enough. So we can optimize an operation. The other chart here on the bottom try to show you about the stability happening, result of changing the permeability inside the liquid pool, or the permeability change between the producer to injector. So in a lot of cases, once the injector permeability is low and producer permeability is high, you start having instability happening. And in those cases, flow control device have to choke more. So this red line is for subcool of 0. And this one is, the blue one is for the representative subcool at this case, okay? So the red parts have to be above this, and blue parts have to be above this. So in this case, nothing happening wrong other than this point. This is a risky one only. But as you see, other parts are fine. And if you go versus time, we see some cases coming down, and that's the same case. So other than one point that there is maybe some challenges, the other cases are fine. And we have a flow regime. And in this case, we run the Bagspree, and it's pretty simple. And because we don't have a lot of seam, everything's happen here. There is no gas liquid holdup. These are not 1. These are numbers close to 1. But because it's a log scale, everything looks here. So for the multi-phase modeling, we're always looking for transition zones. So if something's happened here and something's passing here, we probably shaky on inside the tubing, or we have to watch the modeling if these cases are fine. The last thing is QAQC of the modeling have been done. So the blue turquoise type color is this coefficient of variation of the oil flux, and the red one is coefficient variation of the temperature flux, the temperature distribution. So this is based on the history. So this is based on the field data, and this is the model one. So software tries to use the temperature flux, temperature distribution to model the oil flux. And if variation looks the same, not the numbers, in this case we're looking for up and downs. So we have up here, there's up here, we have up here, yeah, a bit up here. And we see the trend is pretty consistent with what's happening instead of this part, which is early time. Then we can say, all right, this modeling is fair modeling. And last, I'm gonna just talk about just kind of talk about the main features in the SAGD model in the Ashaw package. It models for instability. So the model Conin 1 and Conin 2 is based on the flashing and instability happens. So it's instability modeling. It honors the heat transfer and reservoir dynamics. It modeled the open flow of the completions and the convergence skin. It has an automated history match, which we didn't talk in this case. In the future, for the erosion example, we're going to talk about this history match. Options, circulation and bullheading module, which we didn't use it here, but there will be one example. We're going to talk about erosion and PSD particle size distribution that been used for erosion modeling, and diagnostic chart, which we briefly go over it. And this is the overview of the models inside Ashaw and the future development. Currently, we hardly work on the gas tank to have the Langmuir effect and vertical section wrap up. And in the future, we will have a SAGD infills and CSS. And we're also working on to wrap up the experiment module, which model the erosion experiments using the boundary layer and using the CFD modeling to see how the flow contour device is reacting, and the network modeling for better red perm representation, and developing the better boundary element models for interaction between the wells in the future. Thanks for listening to this example. Hopefully in the future I provide you better examples, and it raised some interest in using the Azure package.